Hey folks, it is day one of our fourth unit. We are studying differentiation now. Today we're going to be talking about visual derivatives. We have two objectives. We want to define what a derivative is, and we want to actually sketch some derivatives as well. So let's get started. But before we actually get started, I want to remind us of something we have already done this year. Let's think about how we will sketch this function. So notice it is factored, and so I can easily identify all the zeros. I'm going to have a 0 at the x value of -3, +2, and +5 from those three factors. And now I want to sketch this function, so notice it is a cubic function with a positive leading coefficient. So I know my end behavior is down to the left and up to the right. So if I sketch this in, the graph's going to look something like that. So if I think about this function, I want to identify the intervals of increase and decrease. Well, at this point, I don't know how to do this without my calculator. But remember, we would find those maximum and minimum values there. We would find the x values, and then we would say that this area to the left is increasing, because as you move to the right, your graph goes up. This area in between the relative maximum on the left and the relative minimum on the right, that is decreasing, again because our graph is going down there as we move to the right. And then finally this last section is also increasing because we're moving up to the right. We will learn later on in this unit how we could figure out those intervals, the x values of those maximums and minimums, without our calculators. That's where we are heading, and to get there we want to do some limit problems real quick. So let's remember how we do this problem. We're going to write out this limit as delta x approaches 0. F of x plus delta x is just going to be that function. Instead of x, I substitute in x plus delta x. And so, if I write this limit, I'm going to get 3x plus 3 delta x. Notice I distributed it in that 3 to both terms. Now I want to subtract my f of x function, so I'm going to subtract 3x, and that's all over delta x. Well, notice what happens. I have a positive 3 and a negative 3, so I'm left with 3 delta x over delta x. Whoa, that's an A. I want a delta there. 3 delta x over delta x. And again, notice that I have a delta x in the numerator and in the denominator. So I'm left with the limit as delta x approaches 0 of the function 3, and that, of course, is 3. So let's do another problem now. Same idea. We are taking the limit as delta x approaches 0 of this linear function. So this time, notice we have a negative 7x, and a minus negative 7x gives us a positive 7x. And so I'm left with negative 7 delta x over delta x, and of course those delta x's will cancel out. So I will be left with negative 7. On this next one, I'm going to do the same thing, and I'm going to end up with a 2x plus 2 delta x minus 2x, and then of course plus 5 there, and a minus 5 there as well from that and that. But again, the main idea is all of that is going to cross off, and you're going to be left with delta x over delta x. It's going to cross off, and you're going to end up with that number right there. So this is going to be 2, and this next one is going to be negative 4. So if you notice, every time we took that limit, we ended up with just the coefficient of the x term. More specifically, since we're talking about a linear function, we ended up with the slope of the function when we took that fancy special limit over there. So this limit we've been doing is actually, in calculus, it is called the limit definition of the derivative. And that's what derivative does, essentially. It tells you the slope of a function. Now notice we were looking at linear functions, so it's easier to think about the slope of a linear function because we're used to talking about that. So if we look at these three functions on the bottom, if I were to take the derivative of that first one, denoted f prime of x, that would just be negative 3 halves. Derivative of the second one, g prime of x, would be pi. And derivative of the last one, h prime of x, would be 99. So again, I think it makes sense to talk about slope for linear functions, but what if we have something like x squared or x cubed or, I don't know, sine x or any other function that's not a linear function? Well, then how do you talk about slope? Because slope is referring to the coefficient, the x term, of a linear function. And if we don't have that, well, then what can we do? Well, you can think of each point kind of associating with a linear function, the linear function of the tangent line. And again, a tangent line comes down and touches your graph at exactly one point right there. So you can think about it as we move along this function, the slope of that tangent line changes. That's not a very good looking tangent line there because it shouldn't cross, but maybe something more like that. Notice that at different x values you end up with different slopes there. Notice that black line has a steep negative slope, the red line has a slightly less steep but still negative slope. I could draw another one in here, a blue one right there at that relative minimum value, and that has zero slope, and then that green slope now is positive. So if you think about this function, the slope is constantly changing. So if we were to graph the derivative, f prime of x, it would not just be a number, it would not just be a slope that is a number like we saw in the linear functions, it would be some sort of function. It would need to change. So you need to think about some key values when you're looking at a graph if you want to sketch its derivative. You should think about whether or not the function has any symmetry. Is it odd? Is it even? Does it have symmetry across some axis or maybe two different axes? Does it have maximum values or does it have minimum values? Are there intervals where your function's decreasing as opposed to increasing? And how quickly is that slope changing? So lots of different things to think about, and let's actually use some of those things now to sketch a derivative. So let's look at this function. Notice it is seemingly a quadratic function. It looks like it's been shifted to the right 3, but let's think about what is happening with this function. So I know we just came out of our rational functions unit. Don't get confused. I'm not drawing a vertical asymptote here. I am just separating the plane because I want to, again, think about intervals of increase and intervals of decrease. When I'm to the left of that awkwardly dashed line, notice that my function is going down to the right. So that is a decreasing interval over there from negative infinity up to that point, or really from negative 1 to there, because that's all we see. And then the function is increasing when you are to the right of that. Now, another key thing to think about is that relative minimum value, because right there, where we have a minimum value, the slope of the tangent line is 0. That is crucial information for us. So probably one last thing to think about is if you think about this quadratic function, if you compare that right there, the slope of that tangent line to the slope of that tangent line, since we know this function has symmetries, those slopes should be the same but opposites. And then one more thing to compare that to, if you compare that one of those blue ones to, say, a black one up here, we know that the black slopes are going to be greater than the blue slopes because of how we know the function y equals x squared looks. So let's piece all that information together now. Remember, we're sketching the derivative of this function. So if we say that the blue function was f of x, we are going to sketch f prime of x, and again it's just denoted with an apostrophe there. But let's piece it all together. So to the left of that dashed line, I am decreasing, which means my slope is negative. So I know that to the left of that line, I have to be in the negative world for y values. To the right of that line, I have a positive slope of those tangent lines, so I need to be positive. So I know I'm up there and down there. And then finally, if you think about that absolute minimum value there of the blue function, well, that slope is 0 there. So at that point, my derivative has to actually cross the x-axis. So I know I'm positive here and negative here, and I know I have symmetry, so whatever it is doing, I'm going to clean this up a little bit, whatever it's doing on the right, it should also be doing on the left. And I just erased all my function on accident. But it should look something like that. Increasing intervals are going to represent a positive slope, so positive y values. Decreasing intervals are going to represent a negative slope, negative y values. And relative maximums or minimums are going to represent zeros of your derivative function. Compare this one to our next one. It's essentially the same thing, more or less. At least it looks like it is. Look pretty similar, right? But it is upside down, so everything is essentially going to be flip-flopped this time. Now we are increasing over there and decreasing over there. Our 0 is still going to be in the same spot, but now I'm going to have to look like that instead because my increasing and my decreasing intervals were flipped. So notice how the equation of the derivative changed there. Let's try a function now that looks cubic. Let's take both of these maximum and minimums there, where the slope of the tangent line is 0, and let's give ourselves zeros for our function. And then let's think about the other information. To the left of that left 0, my graph is going up, so I know I am increasing there, so my y values are positive. In between my two zeros, my graph is going down, so I know I'm negative there. And then finally, on the right of that other 0, I'm again going up, so my graph has to be positive. Now, another good thing to think about is if you think about this function from that 0, when it moves to the right, this graph is curving down, and then at some point it stops curving down and starts curving back up like that to come down to that minimum value right there. That is called a point of inflection, when it changes from a concave down function to a concave up function. When it does that, we get a special characteristic of our derivative function. If you think about it, if you think about these tangent lines, so if you think about the slopes of all these tangent lines in between there, because of the shape of the graph and the changing concavity, if you think about the slopes of those red lines, they're fairly shallow. The blue is steeper, and then at that point in the middle, it is as steep as it ever gets, because then it starts to curve back the other direction. And so that point in the middle, that point of inflection, is going to represent the largest value for that part of the derivative there. So in this case, since it's negative, that's going to represent the most negative slope it ever hits. So that's going to be a relative or possibly absolute minimum on our derivative function. So let's sketch that on there. We don't necessarily know at this point where it should be, but it should be a minimum. And so again, we've got our positive and our negative areas and our zeros. So we can now sketch in this derivative, and it's going to look something like that. So let's do one last one. We'll identify our minimums and maximums. Look to be somewhere around there. We can identify our intervals of decrease and increase. So here we are decreasing. In between the zeros we are increasing. And then on the other side here we are decreasing again. So that represents again positive and negative portions of my graph. And also let's think about that point of inflection where we're going to have a minimum or maximum on our derivative. That looks like it's going to be happening somewhere right around there. And it's going to be maximum since that is in a positive section. So I'm going to look something like that. Pretty neato. So one quick question to think about. If you look at this function, notice they all seem to be parabolas centered on the y-axis. So they have symmetry to the left and to the right. They are all decreasing to the left, and they are all increasing to the right, and they all have their minimum values at 0, and they look to, be fairly similar, so they're all going to be functions that have derivatives that look like this. We can't say for certain if they're exactly the same, but they're going to be pretty gosh darn close. So let's sketch this last one in. Again, anywhere we have a relative minimum or maximum value, that's going to correspond to a 0 on this graph. So something like that. And then in between there, let's label positive and negative sections going by the slope. Well, to the very left there we are decreasing, so we're negative. In between those next two we are going up, so we are positive. In that next section we're going down again, and then in that section to the right we are again increasing, so we're going to be positive. Now let's go ahead and see if we can identify some points of inflection to mark those on our graph as well, and I'm now going to put them in there. Notice we have a negative one there and a positive one there. And now let's sketch this all in. Starting to the left, I am negative. I'm going to hit those zeros and then hit that maximum value. So I'm going to look something like that. Come down, hit my next 0, and that minimum value right there. Hit that 0, and then go up to the right. And I am done. So as we move forward, I want you to start thinking about degree of functions and how that relates to the derivative. Because think about the two shapes of these graphs here. We have our cowboy hat, and then we have a cubic looking function. So think about how those relate.